Hello, welcome to my classroom. Our next topic under soil water is infiltration. We have already discussed process of infiltration. Now, what are the factors which determine the infiltration rate of the soil? Uh, for a non-soil scientist, it will be very easy. He or she will say that okay, infiltration rate will be fast in coarse texture soils. It will be very slow in fine texture soils. So that's all. But no, the infiltration rate of the soil is determined by so many factors. So we will be clubbing these factors under four categories. So first category is profile characteristics. Characteristics. Since I told you that this is the process of entry of water into the soil, so of course the surface conditions of the soil will determine the rate at which the water moves into the soil. So first of all, yes, very important is soil texture. So in general, coarse and medium textured soils have higher infiltration rate than fine textured soils. Okay. So we know that why? Because in coarse textured soils, you have a dominance of macropores, and macropores are basically water transmission pores. Whereas in fine textured soils, it's dominated by micropores, and micropores are water retaining pores. So when you have dominance of water conducting, water transmission mission pores, then of course the movement of water will be fast. So that's why the water moves very fast in medium and coarse textured soils than in fine textured soils. But then one more factor is there that if you have a coarse and medium textured soil, aggregates are very weak. And particularly, this is more true when rainfall is there. When rain falls, it has a kinetic energy, raindrops, and higher the intensity of the rain, more will be the drop size, and more the drop size, more will be kinetic energy. So ultimately, raindrops, they break down the aggregates, they disperse the aggregates into finer particles. Those finer particles, some of which may be even the primary particles, they clog the surface of the soil, and maybe in such soils the infiltration rate, though initially high, it may decrease with time, and it may be the infiltration rate may be lower even from that of the fine textured soil. So this is one condition you have to keep in mind. So whether if of course, yes, if it's a sandy loam soil, if it's a coarse or medium textured soil, but organic matter content is very high, or you can say the cementing agents like sesquioxides, like carbonates, bicarbonates, they are high. They bind the aggregates strongly, and aggregates may be strong, may not broken down. But in case where the aggregates are weak in fine textured soils or medium textured soils, maybe then that the infiltration rate during later stages may be lower than that of the fine textured soil. Very important point. Generally, we say that okay, it should be always higher in sandy soils than in clay soils. So, soil texture is there. One thing is, yes, in general, but you have to keep in mind the formation of crust, because when the aggregates break down, they clog the surface, then kinetic energy further compacts the soil, forms a very few millimeter compact layer which we call as crust. So crusting is more severe in coarse and medium textured soils than in fine textured soils. This is a drawback of coarse and medium textured soils. Otherwise, they are very light soils, very easy to cultivate compared to fine textured soils. So formation of crust, it may decrease your infiltration rate, maybe at later stages when crust is formed. Third phenomenon is that similarly, if you have a fine textured soil, so you are saying that in fine textured soil, Yes, the infiltration rate will be low. But if this fine texture soil is dominated by expanding type of minerals, like you have say montmorillonite, so what happens that these when soil becomes wet, these minerals, they expand, they convert some macropores into capillary pores. And if these minerals are also dominant in coarse texture soil, they may also reduce the infiltration rate. So this means if you have a dominance of expanding type of minerals in either of the soil, in fine, coarse, medium, then on wetting, after the soil becomes wet, then it expands, it converts the it reduces the size of the pores, infiltration rate may decrease. But when it dries, it contracts and it may produce large cracks. And after those cracks, when the soil has cracked, there are big cracks and rain falls. So initially again the rainfall will be, this infiltration rate will be very high. But as the soil becomes wet, then again those cracks they join, they reduce the pore size and infiltration rate may decrease. So this is either way. Texture you cannot blindly say, but again apart from texture you have the strength of the aggregates, weak or strong, in both fine textured as well as coarse textured. And similarly, type of mineral, that you have to see that what type of minerals are present in the soil. So combining all these three parameters, then you can say that yes, if this is a fine textured soil, this is a sandy soil, in which case and at which stage of initial stage, middle stage or final stage. As I said over here, that initially this is initial stage, this is middle stage, and this is late stage, where the rate becomes constant. So this constant rate, this will depend upon formation of crust. This will depend upon the type of mineral you have in the soil. So after soil texture, we have another factor, that is soil structure. Now very simple, that if your structure of the soil is good, that means your aggregates are strong. Again same, where if it's well aggregated soil, then infiltration rate will be higher than compact soil. This is one thing. Second is there could be subsurface compaction also. Generally, in paddy soils, where we puddle the soil, where we till the soil under wet conditions, we have subsurface compaction. And subsurface compaction means you have two layers based on the structure. You have a low bulk density layer, then high bulk density layer, then again you may have low bulk density layer. So whenever there is layering sequence, always the movement of water stops at the boundary of the two layers. So when water stops at the boundary of the two layers, even for some time, few seconds, few minutes, the overall infiltration rate will decrease. So it will depend upon the that. Then again, if it's not a well aggregated soil or compact soil, then again crust formation. If you have a soil, particularly coarse and medium textured soils, those are very prone to crust formation. So in that case, after the formation of the crust, infiltration rate will decrease. Then third is layering. Layering of soil. Now layering, as I said, layering could be because of different textures. You have a coarse textured above, fine below, then again coarse, or reverse, fine above. So this, whenever there is layer because of soil texture or because of soil structure, once the water reaches at the boundary of the two layers, it stops for some time in either case, and when the particular soil matrix potential develops, then water moves, enters into the second layer. So similarly, if water stops, infiltration will drastically reduce. Then again, when water moves to the next layer, it may increase, then again it may decrease. So it's not that always you may get this type of curve. You may have this type of curve also, that infiltration rate may decrease. Over here it is decreasing, then it may increase, then again it may decrease, like this. So layering is very important. Generally we discuss the things when your soil is homogeneous without any distinct layers. Then it also depends upon the amendments which you are adding. Let me tell you the most important amendments and even fertilizers. The most important thing is you might be aware of the sodic soils. In sodic soils, water remains stagnant at the surface of soil. Even if it's a coarse texture soil, the infiltration rate is very poor, because the soil presence of dominance of sodium ions, the soil becomes dispersed, and the aggregates, even if aggregates are strong, they get dispersed, finer particles, they clog the surface, and even those finer particles, even clay particles, they remain mixed with the water. So this is in fact a very important point to recognize a sodic soil without touching it, without testing it in the lab. You can simply, okay, water is standing and this water is muddy. So surely you can say yes, this water, at least if it is standing, it should not have been muddy, because after some time the particles settle down. But because here the process of dispersion is there, so because of the dispersion, the soil primary particles, they remain in the suspension. That's why water is always muddy. And if you add gypsum to such soils, gypsum is calcium sulfate. If you add gypsum, then calcium replaces sodium ions, and again soil becomes flocculated. Then dispersion is not there. Soil becomes particles, they join together, they make again aggregates, infiltration rate increases. So whenever you add gypsum to a sodic soil, you have a drastic increase in the infiltration rate of soil. Similarly, it is being said that if you add ammonium sulfate as fertilizer, ammonium sulfate, it increases infiltration rate than urea. If you add urea into the soil, it may not affect the infiltration rate, but if you add ammonium sulfate into the soil, then infiltration rate may increase. Could be because the sulfate ions, they may be playing a role in aggregation and all that. Then in the profile characteristics, we have microorganisms. Soil is basically a habitat for millions of microorganisms, and many of these microorganisms are very important from nutritional point of view for the plants, for the roots. You know that we add urea into the soil, it's amide nitrogen, it is converted into ammonical form, then it's converted into nitrate form by certain bacteria. So these microorganisms, their food is organic carbon. Whatever organic residues you are adding into the soil, they get decomposed, because these residues are in fact the food for microorganisms. So when microorganisms do this process of decomposition, certain gums, jellies, etc., then some gases, gums and other byproducts, and these gums and byproducts, they basically act as the cementing agents. They make the aggregates stronger. So if the aggregates become stronger, infiltration rate will be better. And at the same time, these gums, they may also block the pores. If they block the pores, then infiltration rate decreases. And so this is in fact very important process. On the other hand, you have microorganisms and other organisms, I should say. And in other organisms you have earthworms. Now we know that earthworms, they make burrows into the soil. So they drastically increase the infiltration rate, which may not be desirable from soil physics point of view. Because a man of water management, he would not like that there should be preferential flow of water out of the root zone. So this may be good. Earthworms, they make the soil fertile, they make the soil porous, but if it becomes too porous, then water will not, will not be stored in your root zone. It will go out of the root zone. So we have to keep this in mind. But if you have a compact soil, for that earthworm population is good. Then it become also depends upon the infiltration rate. Also is a function of initial soil moisture content. This is very important. If you have a dry soil, as I said initially, the rate will be very high, because hydraulic gradient between the upper few millimeter of saturation zone and below you have the dry soil, hydraulic gradient is very high, movement will be fast. But if your soil is having some moisture content, if higher the initial soil moisture content, lower will be infiltration rate. Then this curve could be like this. This curve could be like this, not like this. So because here you have theta 1, here you have theta 2, and theta 2 is higher than theta 1. So if your soil is dry, initial rate will be high. If your soil is wetter, initial rate will be low. This is very important. Then again it depends upon then also one thing is your hydraulic gradient. Second thing is it also affects the swelling and shrinking. If it's a dry soil, then you can expect the shrinkage, you can expect the cracks, and could be the, as I said, theta 1, theta 2. It may ignore this, and the infiltration rate could be higher even in theta 2 because of the cracks. And if it's a wetter and you have a dominance of expiring type of minerals, then it could soil could swell, soil solids swell, and they reduce the size of the pores. Infiltration rate could be lower. So this is how initial soil moisture content affects. Then lastly, in this group of profile characteristics, we have season of the year. So season of the year again depends upon. Now here, yes, it depends upon, it determines the initial moisture content. If you have a say winter season, yes, soils will be wetter than during summer season. But at the same time, if you have rainy season, the soil will be having good vegetative cover. The grass cover will be good. Overall soil surface landscape may have good vegetation cover, and vegetation, it protects the soil surface, so it will not let the crusting be there. So somehow it will determine the infiltration rate of the soil. In the same soil, you can record infiltration rate during summer season. Yes, it could be higher during spring season, winter season, when the soil is comparatively moist, it could be lower. So this is again an important fact. So this was first category of the factors affecting infiltration rate, that is profile characteristics. Now some of the characteristics are water properties also, because it is in fact the water which is moving into the soil. So its properties will also determine the rate at which it is moving. So can you tell me the first important point in this? It could be, first is sediments. Generally, the source of irrigation could be canal water, it could be tube well water. Tube well water is clear, canal water is generally with sediments. When you are applying canal water to the your fields, and the sediments, they get settled down, they may clog the pores. So these sediments, they clog the pores, and decrease the infiltration rate. Then you may have presence of salts. Now on one hand you have saline water, on the other hand you have what you call as non-saline water. So when you have salts present in it, it increases the viscosity. So salts, they increase viscosity, and higher the viscosity, lower will be the movement of water, what we call as fluidity. So all those factors which affect fluidity, they will come over here. So viscosity, so lower will be infiltration rate. Third will be the presence of sediments, or yes, temperature of the water. Higher the temperature, high temperature, it reduces viscosity, and if viscosity reduces, movement of water becomes faster, less viscous, so infiltration rate increases. This is how the properties of water they affect. So basically all these we have studied already under the term fluidity, and these are the permeability. So permeability, fluidity, these determine the hydraulic conductivity, and hydraulic conductivity determines infiltration rate, movement of water, flux, and flux determines the infiltration rate of water into the soil. Then rain characteristics. Third category is the rain characteristics. Now, as I said, first of all, rain intensity. R5. There is direct relation between rain intensity and drop size. D50 is median drop size. Median drop dia. Median drop dia is that you have a spectrum of raindrops, falling. Some are bigger, some are smaller. So this is the median dia. 50% of rain falls with the raindrop dia less than this. 50% falls with raindrop dia more than this. That's why we take a middle value, D50. So higher the D50 means there is more, more number of bigger drops, and bigger drops means their mass will be more. Mass means 1/2 mv square, so kinetic energy will be more, velocity will be more. So higher the kinetic energy, more will be the disruption of aggregates, and this is how disruption higher D50 means higher kinetic energy, okay, means higher dispersion of aggregates, and ultimately lower infiltration. This is how the things go. Then again it depends upon that if your rain intensity is less than infiltration rate, that means the speed with which water is falling on the soil surface is less than the speed with which water is entering into the soil, there will be no stagnation. Okay, so this is expected that whole of the rainwater will infiltrate into the soil. This is good, our profile becomes recharged. But on the other hand, if your rain intensity is higher than infiltration rate, then there will be stagnation of water. When water stagnates at the soil surface, there are chances that it may move out of your field, so it could be runoff. So this may lead to runoff generation, and more the runoff, lesser will be the infiltration. And then again, rain, it increases soil water content, it increases your vegetation cover, it increases your earthworm population. So all these things, you can yourself guess that how these things will affect the infiltration rate also. Last category of the factors affecting your infiltration rate, that is the land characteristics. Again, very important. Land characteristics. Now here you have a flat surface, so little or no runoff. If you have slopy land, then there will be more runoff. So that means on a slopy land there will be less residence time. When residence time of water on the surface of the soil is less, then infiltration will be less. More water will go as runoff. So here runoff will be higher. So higher runoff means infiltration rate will be less. So this is one effect. First is slope steepness. Second is roughness of the surface. Now I'll give you over here a simple example. If you have a freshly cultivated field and rain falls, so we expect that most of rain enters into the soil because you have opened up the field. You have a dominance of very bigger pores, macro pores, large macro pores, so water will infiltrate. On the other hand, imagine a field at the end of the harvest. So this is comparatively less rough, and you have a lesser number of macro pores. Infiltration rate will be less. Number one. Number two, if you have a rough surface, on the other hand, you have a smooth surface. So if clay soil is always having rough surface, when you till it, its surface becomes more rough. Roughness coefficient is higher in a clay soil than in a sandy loam or coarse textured or medium textured soil. So when water moves from one end of the field to the other end, the movement of water will be faster in coarse and medium textured soil than in clay soil, because here you have freshly tilled the soil, surface is rough, roughness coefficient is higher. On the other hand, in coarse and fine textured soil, roughness coefficient is less. So when roughness is less, the movement of water will be fast, and fast movement means infiltration rate will be less. Yes, in this case, when roughness coefficient is more, residence time is higher, infiltration rate will be higher. So again, one more important is vegetation. It also depends that whether your land is vegetated or it's bare. If it's having vegetation, you can simply see that if you have a grassy land and rainfall is there, so water does not stagnate. On the other hand, you have a bare soil, water generally stagnates over there, because grass protects the soil from crusting. Number one. Number two, the roots of the grass, they make the soil porous. Infiltration rate is higher. With the same texture of soil, this is how the role of vegetation is there. Similarly, instead of grass, you could have any type of crop cover. So crop cover always protects the soil from crusting, and infiltration rate could be higher provided land slope is similar. So these are some of the characteristics factors which may affect. So four categories: profile characteristics, water characteristics, rain characteristics, and land characteristics. So I hope the things are clear. Thank you very much.